So, good morning, everybody. Welcome to this special session on the 22nd of February Christchurch earthquake in New Zealand. And welcome not just to the people in this auditorium here this morning, but welcome to people wherever you are, because this session is being webcast. I'll just say at the outset also that there'll be a poster session for this event here about Christchurch. If you have any posters, you can just take them and put them up online on the boards tomorrow, and it's between XY 5500 and 599, 10:30 to 12 o'clock tomorrow, that's Friday. And now I'm just going to hand over to Dong Dingwall, President of EGU.
Thank you very much, Mary, and thank you as well for taking the initiative together with Dr. Kravchik for this session. We always try to react to events even at a very late stage in the organization of this meeting each year. And of course, as a geoscience society, we take our responsibility when it comes to such recent events very seriously. We are joined this morning by the ambassador of New Zealand to Austria and to Slovenia and Slovakia, as I understand. And we welcome him, Mr. Ambassador Griffiths, His Excellency Mr. Griffiths. And I would just like, I've had a very interesting chat with him just now, and I think he grasps the context of this meeting and is very happy to be able to be here. When scientists react to catastrophes, it can be seen in different ways. You can sometimes think that scientists see such major events simply as opportunities, but there's a funny thing about the way that scientists think and work. They don't only think and work from the head, they think and work from the heart. They're in it with all of their energy. And so in a way, it's also an expression of solidarity and sympathy in the wake of this catastrophe in terms of human life, in terms of damage to the economy of the area, that we express when we stand up in sessions like this and say we are going to continue to put all our energy into wrestling these kind of beasts to the ground. And in this context, I hope you'll be able to appreciate also the science which is going to be presented here today. Thank you very much.
Thank you. So the first talk will be given by Caroline Holden and others from GNS in New Zealand. It's called an overview of the MW 6.3 Christchurch earthquake and a preliminary source mechanism.
Okay, so good morning. I'm presenting today an overview of the magnitude 6.3 Christchurch earthquake that occurred last February 22nd in New Zealand. This is collaborative work between myself and many other colleagues. My talk will go through, will bring you a bit of background about this earthquake, then we'll go through some illustration on how tragic and destructive that earthquake was. And finally, we'll go through some source model from the GPS and INSAR dataset, as well as some strong motion dataset. Okay, so New Zealand is a very seismically active country. It's been stricken by a lot of major earthquakes for the past 100 years, and a remarkable one was the 1931 Napier earthquake. It would be hard to show from that angle. Yeah, that struck Hawke's Bay in 1931 with a magnitude 7.8, and it was the most tragic earthquake in New Zealand, with 256 people that lost their life. One to note is the Wairarapa earthquake in 1855 that had a magnitude 8.2 and rose Wellington by a few meters. So definitely some serious earthquakes in New Zealand. And the reason for this is that the country is straddling a plate boundary. On the western side, you've got the Australian plate, and on the eastern side, you've got the Pacific plate. And both those plates converge at a rate of about 4 centimeters per year. In between those two plate boundaries, you've got the Alpine fault, which ruptures regularly in very large earthquakes. So the recurrence interval is about 300 years, and the last one was about in 1700. So this is the location of the Christchurch earthquake and of the main shock, the Darfield earthquake that occurred last September. And this earthquake occurred in a region of relatively low seismicity on previously unmapped fault trace. Okay, so just talking about the main shock quickly. The main shock was a very large earthquake, magnitude 7.1, ruptured a 40-kilometer-long fault trace to the surface with an average slip of 2.5 meters, peak slip displacement of 5 meters, so a very large fault. It strongly shook the Canterbury Plains with PGA of 1.6 G near the epicenter, and it was felt strongly all around Canterbury. It was a destructive earthquake as well, and it destroyed earthquake-prone buildings such as unreinforced masonry buildings, such as this house here, heritage buildings, and it caused a lot of liquefaction as well, and the liquefaction caused damage to residential area from lateral spreading as well as from to lifeline systems. However, this wasn't the last earthquake Canterbury would hear about. 5 months later, they were struck by a 6.3 aftershock. This map shows the rupture, so in green, you've got the main shock, the Darfield earthquake in September, as well as the fault trace that ruptured during the earthquake and the secondary fault source below the surface. You also have aftershocks for that earthquake in green all the way up to February 22nd. You can see on the eastern part of the fault trace the 6.3 earthquake with the suggested fault trace, subsurface fault trace of 10 to 15 kilometers. And this earthquake has its own aftershocks, obviously, and the aftershock sequence was very rich in very large aftershocks, a few of magnitude 5 plus. The Christchurch earthquake was felt all throughout the country, as you can see on this map of intensity, and it was felt obviously very strongly in Christchurch and its area with 8 reported. Okay, so now I'm going to go through a few slides to show how dramatic and destructive that earthquake was. Obviously, there was extreme shaking. This is due to the fact that the epicenter is located very close to Christchurch, so there was very strong acceleration recorded in the Christchurch area in the southern suburb. There was widespread liquefaction for that earthquake all around the city, but especially in coastal area such as the suburb on the eastern side of Christchurch and the suburb along the course of the Avon River. There were many landslides and rockfalls all around the Bank Peninsula part that was very close to the epicenter. And there was a lot of building damage widespread around Christchurch, but especially in the downtown part of Christchurch. So talking about the extreme shaking, we've recorded some amazing values of acceleration. Near the epicenter, we've got a recorded acceleration of 2.2 G. We've got 1 plus G in Littleton, 1.8 G north of the epicenter. In downtown Christchurch, we've got average value of 0.5 to 0.8 G, so really extreme accelerations for that earthquake. Now, liquefaction was widespread, and its consequences was extreme flooding of suburbs, was lateral spreading as well. That didn't happen during the main shock, the Darfield earthquake. Liquefaction caused the bank of the river to get closer from lateral spreading by up to 5 meters in some part of the Avon River. And liquefaction caused the burst of sand, obviously, with depositing a layer of 1 meter thick sand in some suburbs. I have a friend who came home after the earthquake half an hour later, and he could still see like bubbling sand volcanoes in his garden. So very impressive sight. Okay, landslide and rockfalls. There were more than hundreds locations of observations of various types of landslides and rockfalls. On this map done by Chris Massey from GNS, you have in green, you've got the shallow slides or like failure of retaining walls. In blue, you have the rock cliff collapses or rockfalls. And in red, you've got deep-seated landsliding, and in yellow, you have tension cracks or rents. So many locations where landslides have happened in various forms. And to illustrate this, this is just one example, but quite a striking one. That enormous boulder came from the face of the Rapaki cliff down up here, and it rolled down the cliff with impact distances sometimes up as 60 meters. So really massive pathways, and went through that house here and ended up in the street down there. And this is just one example. There were many, many, many examples of that type of rock avalanches. Another illustration of the type of rock cliff collapse we have is in the southern suburb of Christchurch, where old quarry sites cliff have collapsed in near residential areas. All right, now we're going to look at some building damage. So before showing you illustrations of the intensity of the damage in Christchurch, I would like to highlight that New Zealand has an extremely strong building code, and if it hadn't been the case, the consequences of that earthquake would have been way more dramatic. So it's 200 too many people that lost their lives, but it could have been way worse if New Zealand didn't have a strong building code. This slide shows the response acceleration spectra. The black lines represents the design level to which engineers have to build the buildings. The black line is for like very important buildings, such as hospitals. And basically what it says is that any earthquake that's below those lines, the building has to stand up, can be damaged, but is not allowed to collapse. However, you can see that for that particular, the 6.3 earthquake, the purple and the pink lines represent examples in downtown Christchurch of the acceleration spectra, and one of them is actually the hospital. And you can see that the level of shaking from that earthquake is way beyond the design level. However, the hospital suffered hardly any damage, and only the earthquake-prone building collapsed in this earthquake. So I would like to emphasize that again. Another striking feature of the response spectra is if you plot the response spectra of a station near the epicenter, and this is the type of shaking you had near the epicenter south of Christchurch. So quite stunning. Okay, so we'll go through some pictures of damage. A classic type of damage is the collapse of masonry facade from the shops, as you can see on that slide here. So unreinforced masonry just collapsed on the street. In that slide, you see that the old buildings here lost all its facade. However, the one next door has hardly any damage. This is an infamous site of a damaged building in Christchurch. This is the CTV building. And another infamous one is the PGC building, where the soft floor just collapsed and pancaked on top of each other. The earthquake caused widespread damage to heritage building in Christchurch, and this is a very famous site, the Cathedral Square, that lost its clock tower after the earthquake. And also, due to very strong vertical accelerations, a lot of houses in the Bank Peninsula in the hilly part of Christchurch had all the roof tiles toppled after the earthquake. So it's quite a striking sight when you're driving along and you see all the tiles have been completely disturbed. Okay, and just to emphasize what I said earlier on, this is a heavily retrofitted masonry building, and it suffered hardly any damage from that earthquake, even though the shaking was really intense. And a rough estimate from my colleague that about 20% of buildings have suffered severe to collapse type damage. All right, so we go to some source modeling. This is the work from John Bevan and his colleague on modeling the source of that earthquake using GPS and INSAR data. This is an interferogram from data taken before and after the earthquake. Each color cycle represents 1.5 centimeter of displacement towards or away from the satellite. At the bottom part of the slide, you can see that the satellite was traveling north and it's looking eastward. You can see that the coherence of the fringes is really good north of Christchurch and south of Christchurch in the Bank Peninsula region. However, in downtown Christchurch and the eastern suburb, there's a lot of incoherence in the fringes due to ground failure and building failure. Okay, so this is the unwrapped accelerogram. This time we can measure directly the permanent displacement of that earthquake, and you can see that the red spot south of Christchurch, south of the estuary, is showing up to 30 centimeters towards the satellite, and the northern part is showing subsidence up to 20 centimeters away from the satellite. So using this data and we measured GPS point, John Bevan came up with a model for the source of that earthquake. So on the top left, you can see the slip model from John Bevan and his team, and it's composed of a variable slip distribution. The main patch is an oblique thrust patch with up to 2.5 meters of displacement, and the patch next to it is mostly strike slip with up to 1.5 meters of displacement. That model brings the slip quite shallow, very close to the surface, up to 1 kilometer below the surface, and it's the strike and the rake of that model is consistent with the focal mechanism from the regional moment tensor solution. On the right side of that slide, you can see the GPS measurement as well as the modeled one, the computed one from that model, and you can see the bit of discrepancy for some stations, and this is likely to be due to ground failure close to those stations. Okay, on the left-hand side, you've got the observed interferogram again unwrapped, and on the right-hand side, you've got the residual between the observed and the modeled interferogram. You can see the change of scale in between. However, there's a strong red spot south of the estuary on the residual that is likely due to be from an aftershock, and the blue residual on the right slide is still unexplained. Okay, so using this proposed model, John has computed vertical displacement for Christchurch and its area, and knowing vertical displacement after the earthquake is really important in order to reinstore, to fix sewage water system as well as stormwater system. And from John's model, you can see that they were up, so this is the contour plot. They were up to 45 centimeters of displacement, positive displacement south of the estuary. And north of the estuary, you've got up to 15 centimeters of subsidence. So now we look at the source model from the strong motion data. The GeoNet network has been recently developed in New Zealand, and it's a network that's been developed in order to monitor natural hazards in New Zealand, such as tsunami, volcano, earthquakes, and landslides. In Canterbury, we have two types of instruments. We have the national strong motion stations, which are in dark green squares, and we have the recently deployed CNTV.at regional network. Both networks are composed of strong motion stations. And the CNTV.at network has only been in action for the past 4 years or so. And so it was actually there for the Darfield earthquake in September, and it was there for the Christchurch earthquake, which gave seismologists an amazing set of strong motion data with very, very near source instruments. And even for the Darfield earthquake, we even have stations right on top of the epicenter. So an invaluable set of strong motion data. Okay, so the strong motion modeling has been done using 15 stations, 3 components integrated into velocity and with a frequency bandwidth up to 1 Hertz. The stations have used the closest stations, which is within 25 kilometers of the epicenter. This model has only been done using forward modeling tests. We had some timing issues with quite a few stations that has been now corrected, and we'll be able to do some proper source inversion. So this is the model in more detail. It consists of just a simple patch of 10 by 10 kilometers, rupturing quite shallow, and with an oblique thrust, so a rake angle of 130 degrees. It's characterized by quite a high rupture velocity of 3 kilometers per second, and the peak slip on that patch is 2.5 meters. And another characteristic of that model is the direction of the rupture. The rupture ruptures from down below to up deep, so basically towards Christchurch. If we look at the waveform fit, we have really good fit with just a simple thrust patch, reverse faulting patch. We have excellent fit on the far field, but on the further away stations. However, for the near field stations, the ones that are very, very close to the epicenter, we can see that there's some detailing that we're not able to catch with just a simple reverse patch model. So there's definitely another asperity that's smaller than the thrust. So it's consistent with the model proposed by John Bevan. Okay. And this is my last slide. I just wanted to highlight the difference between those two earthquakes. They occurred in quite similar locations. One was the aftershock of the Darfield earthquake. So different magnitudes, smaller magnitude, smaller size of fault rupturing. One was 40 kilometers long with up to 5 meter slip. The other one was 10 kilometers, maybe 15, with 2.5 meter slip. However, the consequences for Christchurch were very, very, very different. In terms of liquefaction, the first one only, just to give some figures, brought 30,000 tons of sand in the streets of Christchurch. This one brought 150,000 tons of sand that had to be cleaned from the streets of Christchurch. And in terms of the building affected as well, the latest earthquake affected more than 400,000 buildings in Christchurch. And in terms of the total cost as well, the latest earthquake has a total cost of about 15 billion New Zealand dollars. And just some acknowledgement. Thank you very much.
So there will be a question and answer session after all these talks today. We'll have 20 minutes or more for more general questions. So I'd just like you to ask questions of each speaker that are specifically about the presentation they've just given. So do we have any questions for Caroline?
Yeah, it's just very technical. It concerns the rake variability. Did you check if this rake orientation, the oblique rake, is consistent with a uniform pre-stress, considering the fault geometry and the stress, tectonic stress orientation?
Yeah, it's consistent, and yes.
So it is just a single asperity that was loaded on this particular geometry.
The big picture seems to be thinking it's just a simple asperity. However, we can see some complexities in the secondary sources, yes.
Any other question at this point? Okay. In that case, thank you very much indeed. So the next presentation will be given by Bill Fry, also from GNS in New Zealand. And he's going to talk about the rupture processes and the strong role that they play in the high peak ground acceleration.
Good morning. I'm sure you're aware by now that these types of events require a response by a very large number of people. So the list I'm showing here at the bottom is in no way comprehensive. We're actually pressed with the importance of dropping our other research activities and focusing strictly on events like this to try to understand the earthquake in terms, in a context that can help the people rebuild and start getting on with their lives. I'll start by giving you a very quick overview of the tectonics, just in so much as they relate to the strong amount of shaking experienced in Christchurch. Then we'll spend most of the time looking at the nature of the recorded wave field and the possible reasons for the high accelerations that were recorded. Then we'll talk about the loading of other faults, so the likelihood of other faults, or what we can actually say about the likelihood of other faults being triggered as a result of the Christchurch and the Darfield earthquakes. And then we'll look at conclusions. This is a schematic showing the mainly paleoseismologically determined rates of movement on different regions of faults across New Zealand. So Christchurch is, Banks Peninsula is down in this region. Christchurch is here. This is the west coast. These are the plains and then the Alps. you see a lot of motion is taken up along the Alpine Fault, which fails very catastrophically, and the Hope Fault up here, and then some of these faults like the Porter's Pass Fault, which have displacements of about 3 millimeters per year. And now we know actually that the Canterbury Plains, just from the Darfield Fault that ruptured in September, take up about 0.2 millimeters per year. So while this is a very, very small amount compared to something like the Alpine Fault, we've seen that if you give sufficient time to build up stresses, it can actually be quite damaging. So we need to be concerned about smaller sources like this as well as very, very large sources like that. This is actually an offshore image, mainly offshore. You see in the far left of the plot, you see Banks Peninsula right here, and then this is the coastline of New Zealand. And this is offshore data showing a series of normal faults that are actually probably trending underneath the Canterbury Plains. So to say that we didn't know about these types of faults is a bit misleading, because we understood that there were these east-west trending normal faults that might be reactivated, extending beneath the plains, but of course we have the sedimentary cover over the plains, so we can't see those faults. This is a plot of the very, very rich aftershock sequence. It's color-coded according to time, from the colder colors being the older events to the most recent aftershock sequence from Christchurch. Overlaying on that is a very, very complex model of multiple faults that contributed to the September 7.1 event. And a key feature that I'll come back to at the end of the talk is this lineament that you see up in Christchurch here in this kind of yellow and green color. So we see actually, as we would expect, the aftershocks extending out through time, and then there's been a dominant extension toward Christchurch. This is an aftershock forecast model. It shows a number of aftershocks of M 4.0 or greater since the September 7.1 event versus date on the x-axis. The top black curve is actually our standard New Zealand aftershock forecast decay model, and the stars are the data from this event. So we have probably a complete catalog up to a magnitude 4. And you see that early on we were actually quite underproductive in the sequence. So we were predicting way more aftershocks than we were actually getting. And based on that, we had revised the aftershock decay model down to this green line. But since the February 22nd event, we've actually jumped back up here. And this plot's even now a bit dated. And we see that we're actually following this trend of the expected aftershock sequence decay quite nicely. So all in all, if you take the whole event and all of the aftershocks, it's behaving pretty much according to what we expect. This is a plot from the south to the north along the eastern seaboard of the South Island, showing relocated seismicity, so seismicity that's been relocated with a very precise 3D velocity model. And all I want to point out here is that, say, if you're going from north to south, up through Christchurch, you see this reduction in the depth of seismicity. So we think that this is probably effectively a thermal perturbation underneath the Banks Peninsula, and it's certainly affecting the crustal structure and the crustal strength. And this is a very schematic cross-section. These are the two nodal planes of the September event, and then the February 22nd event would have happened just up in here, but they happen up in this layer of gray Wackian schist that's probably underlain by something that's already been dehydrated and very rigid. So all in all, this acts as a very rigid body with a very high strength, so it gives rise when it fails to high stress drops. This is a diagram of the probable rupture plane. It ends somewhere between 2 and 1 kilometers beneath Christchurch. The sense of displacement on these two circles is actually reversed. But underneath Christchurch, there's this layer of volcanics that extends out from Banks Peninsula. We're a bit uncertain about the bottom of this layer, but it almost certainly rests on top of this gray wacky basement and extends underneath Christchurch. You probably have about 600-700 meters of some sort of stratified sediment, some sort of low shear wave velocity material. And then you have this material in the Banks Peninsula volcanics, which actually has a very low VPVS ratio. So we're a bit uncertain what would happen when you had this massive slip so close to the surface, some 2.5, maybe 3 meters of slip here, when you actually hit the base of these volcanics. We're certain, though, that the mechanism was an oblique thrust. We know this from regional moment tensor inversions, from first motion analysis, from the geodetic analysis that you've just seen, and from aftershock mechanisms. I was shocked when I first saw this at the regularity, actually, of these aftershock mechanisms. So you see almost, this is the main shock here with a bit more thrust, but if you look at the first motions, it actually has a bit more strike slip. The first motion analysis looks more like most of these focal mechanisms, but they're remarkably similar across the range of aftershocks. This is probably about for the first week of aftershocks. So now we'll look at some of the recorded seismograms. Actually, before we do that, this is a plot of the vectors of maximum PGA, red in the vertical direction and blue in the maximum horizontal direction. And the scale bar, this is 1g of acceleration in each here. So you see there's probably a domain outlined by this where you get maximum motions in the vertical direction and quite high motions. So as you heard just now, that this is about 2.2 g, which is an extreme acceleration. And there are other areas here where we have over 1g acceleration. And then as you get more distal to the epicenter, you start getting the maximum PGAs in the horizontal direction. The frequencies of the recorded ground motions actually are quite variable, or they have different variable bandwidths of amplification or dominant acceleration. Some of them have very, very high frequencies, more than we would see in most earthquakes. And I'm not sure if this is because it was recorded better than most earthquakes are recorded, or other features of how the earthquake actually happened, or it's more likely a combination of all of them. So we see dominant frequencies sometimes greater than 10 hertz, 10, even 15 hertz. And we also see low frequency oscillations at between, say, 5 seconds and 1 second periods. This is an example of 3 different power spectra. One that's located just here, very, very close to the fault trace itself, or the epicenter itself. And you see there's a dominant bandwidth of energy between about, say, 5 and about 10 or 11 hertz. We would attribute this to dominantly source processes. In the central city of Christchurch itself, this site here, you see this band of large energy between about, say, 10 hertz and then up to about, say, 16 hertz, which is quite high frequency. So there's probably a significant component of side effect causing this. And then at a very distal site, you see most of the energy on the lower frequency. So this is lower than about, say, 1 hertz. Actually, right after the September event, there was a campaign to put in typical accelerometers, temporary accelerometers around Christchurch and around the Canterbury Plains, but there was also an effort to put in a very dense network of very low quality accelerometers, these QCN accelerometers, which stands for Quake Catcher Network, and they're essentially analogous to an airbag accelerometer that you might have in your car. So they're very low fidelity, but we were curious to see what you could actually get from that. And what I'm showing you here is spectral ratios that were calculated. The top row of all 3, so you have a vertical and then east-west, north-south component. The top rows are all from the low-quality QCN accelerometers. And actually that's 2 rows of, no, that's just 1 row of them and 1 row of them. And then below that, you see spectral ratios that were calculated from our national network sites that are close to those QCN deployments. And the QCN sensors are very, very high noise. And it's difficult to calculate a good spectral ratio from an instrument that has a high noise. So we've actually implemented a methodology first suggested by Aki and Richards in maybe the first or second iteration of their text to reduce the noise. And we see that we can get spectral ratios that look very, very similar to the ones from the very high quality sites that you see just below them. So this has pretty big impact on situations where you want to maybe find on a very, very small scale, block by block nature, side effects or side amplification. And the shaking was actually very directional and component dependent. This is a site up in this region. And the top trace is a horizontal component. and the bottom trace is a vertical component. The first thing you notice is this low frequency oscillation of the horizontal and the higher frequency nature of the vertical component. And then a second thing you'll notice that I'll talk about in a bit more detail in a second is the asymmetric nature of the vertical components, where we get these large spikes in vertical acceleration, and then we get a much smaller but broader trough of acceleration in the negative direction. These are just the Fourier transforms of the signals I just showed you. This is the horizontal component, and you see this dominant energy down below about 1 hertz, whereas the vertical component actually has something, say, between 6 and 10 hertz. So there's a drastically different signal between these components. So why do we get such high accelerations? As we've seen, it's only a magnitude 6.3, but we've suffered an incredible shaking. Well, the one big reason, as you're well aware of, is the proximity. This was so close to town. It probably extended beneath the southern part of town, the rupture plain. There was actually also a very high stress drop. The USGS energy magnitude was a 6.7. For the Darfield event, the September event, there was also a high energy magnitude of a 7.4 as opposed to the moment magnitude of 7.1. There was directivity, or a stacking of energy with a high rupture velocity. So we think the rupture velocity was at least 3 kilometers per second, maybe up as high as 3.2 kilometers per second, 3.3 kilometers per second. There were certainly some basin effects and side effects, and we also recognize something that's, or we see indications that have been attributed before to a slap-down phase or a trampoline effect, and I'll talk more about that in a second. So the effects of high rupture velocity, these are all synthetics with the local velocity model, and I just have these to point out that in some cases, so this is close to 2G here. So just with a rupture velocity of 3.2 kilometers per second, given the asperity patch that Caroline just showed us, we can actually reach accelerations of 2G. And this is the same image I showed you before, but overlaying on that are some accelerograms that I'm going to blow up in the next slide. And the green lines here are actually the 0 lines of the accelerograms, so you see they're quite top-heavy. And the locations of these correspond to these places where you have these big vertical spikes. This station, this one's actually this station, and then this station, and that goes to that. So this is a blow-up of those records. And these are always normalized to 0, so the 0 axis comes out right here, and the noise before you actually get the event. So the first thing you notice is the scale of these. So this goes up to 2, this is 1. So you have about double the acceleration in the vertical, or in the upward direction that you do in the downward direction. And all of these are very similar to that. And again, they're quite spiky with these broad troughs. So what this has been attributed to in the past, it's been seen before in Iwata Miyagi, this earthquake in Japan, as the first place that we explained, as you probably have a separation, or at least some sort of physical material property contrast at the interface of 2 layers very, very close to the surface. So the energy's going up, and then the lower layer comes back down. It probably comes back down sufficiently more quickly than the upper layer, that you get a tensional force that's stronger than actually the strength holding the 2 layers together. So you get either a slight separation or some sort of change in the physical properties right at that interface. So the lower layer goes down more quickly than the upper layer. And then when the lower layer starts returning back up, you get a slapping of the 2 layers together, and you emit a large amount of energy in the vertical direction. So now we're going to talk about the possible loading of other faults due to these ruptures. So we've noticed since Boxing Day, December 26th, there was an event in Christchurch. Actually, it was over here, and it had its own little aftershock sequence. And we were worried, actually, if you look at the Coulomb failure stress change as a result of the Christchurch or Littleton rupture and the Darfield rupture that I'll show you in a second, you actually load this area quite a bit. So the central business district is located right in here, so we're very, very concerned about even a magnitude 5 event there. And this is a simple static Coulomb failure stress calculation on an event, or on a plane that's oriented in the same way as the Boxing Day event. It's sum, like I said, of the thrust plane from the Darfield or the Christchurch event and the Darfield event, and you see this big lobe of red. So red's bad. This is an increase of about 0.2 megapascals in this region. It's very difficult to interpret images like this, though. It's enticing to see the big red patch and think, oh no, we're in grave danger. But in reality, we don't understand the stress state on a fault. We don't know where in its stress cycle a fault is, so we don't know how much more likely a fault is to rupture because of this. We just know, well, it's probably a bit more likely. So to understand this a little better, we've developed a finite element simulation. And actually, I should acknowledge at this point Brad Agard from the USGS, who's helped out a lot with this. And what you see is just an embedded the solution, kinematic solution from Caroline here, and then some aftershocks plotted around that. And a side view showing the aftershocks we've had, the very well located aftershocks we've had since February 22nd. And what we've done is we've calculated the deformation field from this displacement, and then converted that deformation field just as a first check to see if the model's working into the predicted unwrapped INSAR data. So on the left-hand side is what we would predict just from this finite element deformation model for the INSAR data. And on the right-hand side is actually a difference between what's actually been unwrapped from the INSAR data and our predicted model. And I'll point out that the scale bar on here is very, very small. Compared to this. So this is 30 centimeters, and this is 6 centimeters. So the model is doing a pretty good job of predicting the deformational field. So it makes us think that we can also use it to predict the stress field. So now I have a movie I'll show you with results from that. And I call it a heart movie because to me it looks like one of these images of hearts we see in physiology class. So what this is showing you, stop it. All right, this is 140 degrees. I meant to stop it at about this 130 degrees because, yes, we do know the regional stress field, and the most likely rake of events should be about 130. What you see are plotted are isosurfaces of Coulomb failure stress change. So this is in pascals or 0.5 megapascals. And this is just a color bar for the aftershocks after the main event. So that's why there's such a long period here. And actually, these all fall after the February 22nd event too. So we've tried to explore different ranges of rakes for the future, trying to understand if different fault orientations are more likely loaded or less likely loaded. And actually, this is I should tell you too that the 3D stress model from the Darfield event or the September event was calculated with an Okada routine and just superimposed on this. Or added to the background deformation counted from the finite element scheme. The first thing you probably should notice, though, is that we're not doing a good job of predicting where the aftershock should be. So these things should happen in red areas, but they're not. So we probably need to go back and try to get a bunch of focal mechanisms for these events and see if they're actually occurring in the same way as this occurred. Could we go back? All right, this will be the last slide before the conclusion slide. So why we care about this is we're under a lot of pressure now to say something about the likelihood of continued shaking in Christchurch. So there are people there that want to move back into their houses, or people that want to start reconstructing their businesses. And the Earthquake Commission isn't really sure how to or at what point we should tell them, yes, it's safe to start building. So we have statistical models like this. This is purely a statistical model showing you the probability of exceeding 0.13 PGA in a 50-year time period. 0.13 is probably about where we're going to start to see liquefaction of the very, very soft soils, the class D, these swampy type soils. So what we're trying to do now is we're trying to take deterministic methods like calculating this three-dimensional Coulomb failure stress in a very robust way, and we're trying to combine that with probabilistic methods. So we have some sort of pseudo-deterministic method to tell the bureaucracy when we expect it's probably reasonable to start rebuilding. So to conclude, we've seen very strong accelerations. That's because there's a quite high energy release. There's directivity and high rupture velocity, and probably the slap down phase. We're currently working on modeling to understand the stress state and actually the rupture propagation too. We're working on back propagation methods to see if there is a second asperity from this, where that asperity was, to get more refined estimates of the rupture velocity. And we're working toward these possible pseudo-deterministic hazard models. Thank you.
Right, we can take one question right now.
Just on your Coulomb modeling, is the finite element model connected only to the 6.3 earthquake, or do you superimpose the stress from the 7?
We did superimpose the stress from the 7, but the calculation of the stress from the 7 isn't from a numerical model. It's from using an Okada routine to calculate that. And then we take the 3D stress tensor from that, and then we add that to what we get from the finite element calculation.
Okay, thanks.
Okay, we'll deal with all other questions from Bill's talk in the main question and answer session later. Okay, so the next talk is by Kevin Furlong from Penn State University in the USA, and he's going to be talking about the tectonic and seismological consequences of this earthquake in Christchurch.
Thanks, Mary. Well, thank you all for coming. As you've seen already, this is, although small in magnitude, a very important event and a very damaging event. And so it's important that we understand the context in which it occurred, and if we want to particularly export the lessons we learned from these events to other places around the world. And so this is work I'm doing in conjunction with people at the USGS and colleagues at University of Canterbury, where I was on sabbatical during much of the time that we're talking about. Also, just draw your attention that tomorrow in a session on the geological signatures of earthquakes, I have a talk where I'll go into some of the more detailed of the September event. Now, one of the things, and as Don Dingwell in the introduction to the session pointed out, is when events like this happen, people do look to the science community for some answers. Many of them are answers that we maybe are not the appropriate group or even able to answer, but they are reflective of the types of things that I think people are working on. And I just wanted to bring up some of the questions that I've been asked numerous times in New Zealand about these events, and I think they put into a context the type of issues that we need to be thinking about in our scientific studies. And there's a fundamental question of why is this happening? Why are we having these earthquakes, and when will they stop? Why were they in Christchurch and not in Wellington? I mean, these are the types of issues that people in New Zealand are concerned about. There's questions, people look at the maps of aftershocks and they start seeing patterns as Bill noted in some of the slides he showed. You see these various locations of clustering of events, and people would like to know, are there gaps? Are these gaps going to fill in? How do things link up? And then the big question is it safe? When will it be safe? Should we move back, et cetera? Now, of course, things particularly like that last question are not questions for scientists to answer directly, but we can inform policymakers by providing the appropriate types of information in a way that they can utilize it. So I'm going to have that a little bit as a focus of what I'm talking about. I do want to draw your attention to this lower figure on this that shows part of the problem. I mean, this is a deadly event and a very damaging event, partly because although its footprint is relatively small, it's as though it's a worst case scenario. The regions of strong shaking are exactly in the regions of very high population density. So it's sort of a conflation of those two things. Now, as I think many of you know from some of the previous talks, this is an area where we're looking at a plate boundary regime. The earthquake itself, in a sense, is an intraplate earthquake. It's away from the main plate boundary structure, but it is in an area where there's been internal deformation of the Pacific plate as a result of plate boundary processes. Now, the other thing, though, is that it is not an area that had experienced very many recent earthquakes. This is a map that just shows a year ago, the September 3rd, 2009 to March 31st, 2010, to give you a sense of the fact that there was essentially zero seismicity in the region. This is the future fault. This is the site of where the future fault will be. But the whole region was not experiencing any sort of significant seismicity, so people were not having it on a daily basis. We compare that to the same time interval a year later, and there are literally thousands of events of various sizes, hundreds of events that people are feeling as aftershocks, and it spans a zone that is something greater than 80 kilometers from the foothills of the Southern Alps to the coast and offshore. And so, we go from a regime that was essentially devoid of seismicity to one that in a 6-month period has had substantial activity in a fault zone that is composed of some number of fault segments that are interacting with each other, either in single events or in events that occur as parts of aftershock sequences. Now this is a plot just showing, using the data from GeoNet, the patterns of the main events, the events that sort of people draw attention to, and the aftershocks. So we see, over on the upper left, the Darfield earthquake, and then since then the overall aftershock sequence, and then more recently on the right-hand side, the Christchurch earthquake. But there are other events in the middle there that, for example, this region right here, this is that so-called Boxing Day event, and you can see it has its own distinct pattern of aftershocks, and we see these sorts of things. So superimposed on sort of an overall decay is this pattern of punctuated events, and of course this is one of the things that causes quite difficulty for the people. November, early December, things were quieting down, and then the day after Christmas, whammo, people are woken up again to the fact that they're in an active earthquake zone. Same thing was happening through January, February, and then the Christchurch event comes. So these raise raise questions that folks want answers to. So I want to first focus on the September event, because really to understand the February event, we really have to put it into the context of what drove it. The bigger magnitude 7 earthquake in September. This is the extent of the surface rupture of the fault. It's an incredibly well-documented surface fault. It occurred generally in agricultural areas, very well-maintained farmland, dairy farms, sheep farms, etc. It occurred in the early spring, so the crops had not grown very high yet, so it's very distinct, cut across various paddocks. It's also been imaged both with, visual, but also LiDAR, so there's a very rich data set on the very fine details of the surface rupture response. And so this will become an incredible test bed to be able to see how does a fault within basement interact with, in this case, about 300 meters of gravels, surficial gravels, glacial outwash gravels that will modify perhaps the way it appears at the surface and its remnants. We also, if you look at any, obviously, geologic textbook, you'd see a picture like this for a traditional shear zone with Riedel shears and all the other components. So it's behaving that way. Also, we have an incredible opportunity to get very detailed fault offsets. As we were doing the measurements in September, the comments were made that the fence lines in Canterbury are of geodetic quality. These fence lines were incredibly well maintained, very straight, and so you actually have very precise before and after capabilities, and so as a result, been able to determine the displacements on the faults, both horizontally and vertically on the mapped fault, to probably a few centimeters precision, using kinematic GPS and differential GPS, etc. So we have a very detailed fault map, both of the surface rupture and the details of how that was accommodated at the surface. So we see about a 30-kilometer long segment that's observable at the surface, and the question comes up, is that all there is? For a magnitude 7 event, we were you don't even expect to have substantial amounts of surface rupture necessarily, and so the fact that there was such a well-preserved one was of interest. When we look at the finite fault model, so this is Gavin Hayes' finite fault model from USGS, we see that the section that we observe at the surface, this 30 kilometers of surface rupture, is well modeled in the finite fault model. This area I've labeled surface rupture. But there's a substantial amount of fault that extends both to the east and to the west of the surface rupture, as one would expect typically in an earthquake of this size, that much of the faulting would be subsurface. And in particular, we have this section off to the east that extends another 10 or 12 kilometers with some complication in terms of how it interacts, and that would be off to the east of the surface rupture, closer to the main population centers. We also, when we look at INSAR, and this is a descending orbit picture from the Comet group in the UK, we see that although there's the very detailed fringes, and as was shown before, oft associated with the surface rupture, there's a substantial amount of also surface deformation that we see to the east in the same location as we see the subsurface rupture from the finite fault model. So with that in mind, we think that there's good evidence that the fault that ruptured in September extends another 10, 12 kilometers to the east, offset from the surface trace here, so to the south step over, which also is consistent with some of the strong motion data that was observed in September. Again, as you've seen before, the red are the very high accelerations. There were very high accelerations near the fault in Greendale and other locations, but we also see that there were high accelerations in the Lincoln, Rollston area in the vicinity of where the finite fault models indicate there could be subsurface rupture. Also, I'll show you that this site, Heathcote Valley, which is the one that in the previous speakers noted had the very high acceleration, seems to be not a good location in terms of it's got very strong site effects. Even though it was quite a distance away in the Greendale fault rupture, it still had quite high ground acceleration. So it's a place where the site effects are obviously very important. So with the finite fault model that we have, we can produce essentially a Coulomb fault stress change model. And so this is taking our finite fault model and calculating the Coulomb stresses at 6 kilometers depth, sort of a typical depth of much of the aftershocks. And you see that in the vicinity of the fault, we've reduced the Coulomb stresses. There's still lots of aftershocks because of on-fault processes. There are some key areas. There's this area off to the west end of the fault, very high change. There's this area to the north, but in particular of importance to the people of Canterbury is the area of enhanced Coulomb stress to the east of the September rupture, and in an area that was not at that time filled in. If we look at an aftershock pattern, we can see the things we're going through. We're now getting into November or October. The fault's tending to die out. What you'll see is in mid-December, we'll have that Boxing Day event that will pop off right in downtown Christchurch, very distinctive of linear pattern then. But in general, the aftershock patterns had been dying down. There is our Boxing Day sequence, our events and fade out. And then as we get to February, in another couple of seconds, we will see the February event just light up the eastern segment. So the pattern, I'll just play this once again quickly. We have a lot of events associated with the initial rupture in September. The background seismicity dies down, and we start seeing particularly a fair amount of activity sort of in these areas where the Coulomb stress had indicated potentially an enhanced potential for activity. And then we will see this light up in both the Christmas events and then the events in February. There. So, essentially, filling in the patterns, and when we now put this all together, in a sense from a scientific perspective, the Coulomb models seem to have been fairly robust in terms of estimating where the areas of potential additional activity could be, but of course, as we all know who work in this, they aren't precise enough to say anything about timing or magnitudes, but we can at least identify regions that are prone, more likely or less likely to have enhanced seismicity. And we can see that it's been filled in quite a bit. Now, the questions, of course, came up about, why is the damage been greater? And I think the previous speakers have dealt with the details of that. And of course, it comes to be location, location, location. The footprint of the September event was actually quite a bit larger than the footprint of the February event. But of course, the September event was in predominantly rural parts of the country. where there was not the infrastructure to be affected in the same way. And so when we look at this, we see that the strong shaking, the reds are the intensity high 8s and 9s, and the browns are in the 8s, and we see that it's sort of a bullseye, unfortunately, on the population center of Christchurch. And I mean, it's almost ironic. As the population dies off into the western suburbs, so did the ground shaking very quickly die off. Now, we've seen the photos of the sorts of damage from the February event. It's clearly a very significant event. It did have landslides. It also, I think, has raised questions that we all globally need to think about in terms of land use, as are there appropriate or less appropriate places perhaps to be building. And then the two issues, what does the future hold for Christchurch? And these are the issues we come to, the questions people have. How and when and where to rebuild the city, and are more earthquakes in the future? Well, the rebuilding side, there's the issue of liquefaction. This is data from the backyard of Mark Quigley, a colleague, and you can see that going down to 7 meters, basically the soils are liquefiable to a depth of 7 meters. And so this is large areas of Avonside and all those eastern and northeastern suburbs that have very significant geotechnical issues to be addressed. And these are the areas. This was the liquefaction in that part of town, the yellow map, the Avon River running through it in the after the September event. Mark's sand volcanoes in his front yard. If you now look at the area that was affected by liquefaction after the February event, our yellow map just fits into sort of the little center of this. You can see the curve in the Avon River. Clearly, the areas affected by liquefaction in the February event, because of the nature of the stronger shaking, are substantially larger, and the areas had substantially greater amounts. And so, it's matching the sort of the land use maps that had been produced 5 or 6 years ago, but it does raise the issues of and how to deal with this. The last question is really this one of, are there future earthquakes? And I mean, this is something that we aren't in a position as scientists to answer, but we would like to be able to answer. But I think we can say, we can identify, are there gaps, and are the gaps significant? And if we look at the INSAR data that shows where the major displacements occurred in the two events, we have the INSAR from the September event off to the left. We have the footprint of the deformation as observed from the February event, and there is a region where the two do not overlap. And so that's an area that's sort of the same area here that's between these structures. This is the eastern end of the Greendale Fault. This is the buried segment, we think. This is the approximate location of the February event. But that area is filled by lots of aftershocks. So the question is that to what degree have aftershocks made up for the slip deficits that were not there from the main event? And we look at that and we see that, for example, if we look at fault kinematics, these are a series of regional moment tensors we've produced. The slip vectors and the fault planes throughout, crossing from the west end of this figure to the right, are all very compatible with each other. So whatever the nature of fault slip is in the area, it's got a continuity in kinematics. Whether there's continuity in actually mechanical linkage is less clear. But we can also look at the moment release over time. And so what we have here, the green line represents the moment release from the September event. And then the red line is the moment release in all the aftershocks, including the February event, since the September event. And then the blue line is the sum of the two. And so what we see is the amount of moment release, and this is moment release per 1 kilometer of west to east distance. We see that there's a substantial amount of moment release, slip, in the central section of the fault. We see that then died off as we approached Christchurch. The February event has added about a 50% of equivalent slip to the east. It's, although it's a much smaller event because it's on a much more compact fault, the actual moment release per kilometer is only about 50%. And there is this minimum in the moment release between the two. Now, it's not a zero, it is a minimum. There have been lots of activity, there's lots of aftershocks in that area. And we aren't in a position to answer this yet as scientists, but these are the type questions that people are asking, and we as scientists need to think about how we can help policymakers and decision makers incorporate such advice and information into their decision making. So, and how that will affect the regional stress regime. Here is that stress model from before. This is our stress model for the February event, and you can see that this has now increased the loads in some of that areas that might be the so-called gap, but that some of that was an area that had reduced stress in September. So the balance between the two are issues, and these models as they stand now are too crude to be very specific about the interactions, but these are things we need to improve to be able to make those sorts of statements. So in conclusion, to get back to where I started, the questions people are asking us and the questions that we want to be able to answer, but we really can't quite yet, or we can only to certain degrees. The first are, why are we having these earthquakes? Well, we can say, yes, it's plate tectonics, but people need more information than simply that. We need to get a better sense of locations and timing and magnitudes that are regionally possible. Very importantly, people want to know, when will they stop? And that's a very difficult question to answer clearly. There are the issue of gaps and areas that were not activated but are adjacent or near areas that had major slip during one of these events. And can these gaps host large earthquakes, or simply are they going to have, a large number of magnitude 4s or 5s, which, as we know, can also still be damaging and unsettling, but that's different from another magnitude 6 in the region. And these are real issues that need to be faced. And that gets to the decisions that we as scientists don't make, but we can inform the people who do have to make the decisions of, is it safe and how will it be most safe to rebuild one of the major cities in New Zealand? Thank you very much.
Okay, questions? Any questions directly about this talk? Yeah, here on the left.
I think your point about the regional context is particularly important from the predictive point of view, because you really want to know how this is representing further evolution of the South Island.
Well, yes, it's certainly important. I think it's important also to recognize that, through New Zealand, we have major structures like the Alpine Fault, the major faults going through Wellington, the Wellington Fault, the Wairarapa Fault very close by, the subduction zone off the East Coast. This in no way supersedes the importance of those structures, but it may be a way to probe some of the conditions, like what is the background level of stress within New Zealand, and not just, instead of working from the major structures outward, we have now a technique, data that will help us probe what the regional conditions are like that can then be used to help us improve our ability to work on some of these other structures, like the faults that go through Wellington, the major Alpine fault structures, etc.
Okay, thank you. So our last speaker is Atsori and other co-authors. Good. So it's going to be 2010 and 2011 Christchurch earthquakes, the displacement models and stress transfer from Cosmos SkyMed data. So.
Thank you very much. Good morning, everybody. I want to thank the organizer for giving me the possibility of illustrating the result we got from DINSAR data, and mainly from Cosmos SkyMed data, that is an Italian satellite constellation. This work has been carried out by a team from the Italian Institute of Geophysics and Volcanology, and with collaboration with SARMAP, with a contribution from the Royal Military Academy of Belgium. To point out what I'm going to show you, briefly, I go through the radar interferometry to show the interferograms we calculated for the Darfield earthquake, and then we move to the data modeling, then to the interferogram for Christchurch event and the relating modeling. The stress transfer we calculate by means of this data, and some preliminary result from DINSAR time series. DINSAR technique is widely known. I take the advantages of my of the research that already presented. showing the results from the interferometry. That is a technique that combines in the standard way, two images, one acquired before, another after the earthquake, to show the displacement with centimetric accuracy. And the data modeling I will show to you is a standard data modeling with a nonlinear inversion over subsampled points, and followed by a linear inversion to retrieve the slip distribution over the faults for Darfield and Christchurch event. We show the residuals and okay, that's all. Let me go through. This is one of the available interferograms. This is not calculated with Cosmos SkyMed, but with Envisat, is a European satellite C-band, so every fringe corresponds to about 2.8 centimeters. These interferograms have been generated with Sascape software. I go very quickly through the modeling of this earthquake because it has been already shown by with the previous presentation, and the results are in agreement what we already seen. The fault trace has been calculated by nonlinear modeling, and linear inversion shows peak dislocation up to 8 meters in the shallowest part of the fault, while significant values up to 1 meter are still present at 12 kilometers of depth. We assumed a very simple model, but provided that we will have other images from other satellites and with other wavelength, we will refine this model, but I think that the result is quite stable and won't be so different from this one. We can make some more complicated model, but that's basically what we will find. And the comparison for the Darfield data, for the Darfield earthquake from the observed on the left and the predicted or modeled data on the right, and you can see that okay, the agreement is quite good, and if some high residuals still remain in the proximity of the fault. But let's move to the interferograms we calculated for the Christchurch event. We have two different orbits, one ascending and one descending. These are interferograms calculated with the Cosmos SkyMed satellite from the Italian Space Agency. In this case, we have the one fringes corresponds to about 1.5 centimeters of displacement. And we modeled this data also accounting for possible offset or ramps, because with the satellite we sometimes have problems with the orbits. Of course, when you have two different orbits, you can combine two line of sight, 2 points of view, and this makes the result more robust. The unwrapped interferogram showing what you already seen from the other presentation, some gaps in coherence in the urban areas. The displacement reaches about 40 centimeters in both cases. Just to show you a comparison of the coherence retrieved with two couple of images. The first couple is totally precise, so the two images have been acquired before the earthquake, combined together with another pair of images acquired across the earthquake, and by combining these two coherence maps, you can see the strong change in coherence, and is the phenomenon that you already seen. We don't have data from ground, on field data, but it's likely to be due to the presence of water, of course, and damages that the previous presentation already shown much more in detail. So let's go back to the modeling. The subsampled interferograms we modeled with about 8,000 points, jointly, of course, with a joint inversion from ascending and descending orbits. And this is the model we obtained that is in agreement with what you already seen from the previous presentation. From the nonlinear inversion, we find a fault with maybe a quite different strike. It is 45 degree, dipping 67 degree with a rake of 145, and this strike angle is lower than you already seen from the other presentation, but this allowed us to have some residual a lower level of residual in the area where you've seen here. Sometimes you have the residual higher in this point, but I mean, just this is a model coming only from geodetic data, and by having a lower strike angle, you can have lower residual. The green points have less than 3 centimeters of residuals between the observed and the predicted displacement. And some higher residual in the peninsular area can be due to maybe some unwrapping error. This is much more technical issue. Anyway, now let me go back to the... Okay, the results are consistent. We obtained a peak value maybe higher here, 4.5 meters, located between 3.5 and 6.5 kilometers of depth. This with a joint inversion from both orbits. For this earthquake, we do also modeling with a new algorithm that will be presented tomorrow in the INSAR session with a full resolution technique, but in this case, the result we obtained are very consistent and similar to the inversion with a fixed side of patches, with patches of the same sides. Here, the stress transfer calculation made with the 2 models we obtained. So the stress, the change in stress from the Darfield earthquake to the Christchurch earthquake. These are preliminary, of course, and are based on the model obtained only with 1 interferogram, but as soon as we will have new images, we will improve the modeling, though I think it won't change too much. And there is part of the fault, the Christchurch fault, with a positive value that is in the area of maximum slip 2, loaded by the first earthquake. Then let me show the result we obtained by an advanced technique that is a time series technique that combines together a lot of images to retrieve the mean velocity map across the time spanned by the images. And for each pixel, you can have the evolution in time of the displacement. In general, this analysis is carried out with a long temporal span because Envisat, OERS, ERS satellite have acquisition over the same area every few weeks, every month. With Cosmos SkyMed, we take the advantages of having many images acquired between the 2 events. In this case, for the ascending orbit, we have 9 Cosmos SkyMed images from October to February, and 14 Cosmos SkyMed images from between the 2 events. But the processing of this data takes a lot of time, and these are just preliminary results we got by the time series analysis. So our mean velocity, first time I saw these images, I thought they were there was something wrong. So maybe there are still some problems with the orbits, but first time I saw these images, I realized that there were about 150 millimeter per year of mean velocity. That is a very, very, very strong value. Then if you consider that we are in the time between two earthquakes, this time series account for the post-seismic deformation due to the Darfield earthquake. It means that they account for centimeters of displacement that can be occurred after the first event. And this maybe can give an answer about the gap of displacement, of geodetic displacement between the two events. If you only compare the interferogram, the coseismic interferogram for the first event and the second event, you have, of course, a gap because the patterns are separated. But I hope that by improving the interseismic, I mean, between the two events, we can have an answer about a possible displacement that happened between the two events, and so have an answer about the presence or not of this gap. These are all we have done until now, and our future research will be to strengthen this the connection between the two events by improving the data modeling with new acquisition in L-band with ALOS pulsar images, other MVSAT wide swath images, and improving the time series analysis, taking with particular care for the correction of orbit problems for the satellite. We are looking forward, we take the advantages of this this meeting to have a contact with the researcher from New Zealand to have the possibility of integrating the data I've just shown to you with on-field data to have a better interpretation of of what we are seeing. Thank you very much.
So, questions here over on the right?
I'll just speak loud. I'm good at that. Two quick questions. First of all, do you have data from before the Canterbury earthquake to know if there are effects perhaps due to water withdrawal or recharge? And secondly, have you tried to model the data between the two earthquakes by afterslip?
So about your first question, we don't have Cosmos SkyMed data before the first event. We have Cosmos SkyMed start acquiring a lot of images after the Darfield event. So that's the reason why we got a lot of images after the first event. But we can, of course, there are images from MVSAT satellite and ALOS satellite, but the time, the revisiting time of those satellites are quite large. And we didn't do still a modeling of the interseismic, I mean the period between the two earthquakes because we want to fix the result from time series and then move to a possible modeling, and then it will be an open issue about which kind of model using. So we want first to see which is the kind of displacement we observe by means of time series analysis, and then we will possibly move to a modeling of this interseismic period. Even if you know that in general radar satellite watches in a near vertical direction, in this case we have a strong horizontal component of the displacement. We have to see if we are able to represent this horizontal component. I just want to add an information. I see I have a bit of time. Just a quick information. The incidence angle for the Cosmos SkyMed data is different from the Envisat data. It accounts much more for the horizontal component because we have 40 degrees. So it is much more sensible to horizontal component, and this makes this satellite suitable for this kind of analysis for horizontal component.
Okay, thank you very much. Maybe at this point I should invite the other speakers all to come up here. So just as the speakers are coming, I'll just, we have more people here than we had at the start of the session. I'll just reiterate that there'll be a poster session tomorrow morning in XY between 550 and 599. If anyone has posters or images they'd like to put up, you're very welcome to do so. And also say that this session is being webcast. So we now have all the speakers here, and on the floor we have the New Zealand ambassador. So we'll just open it up now to general questions about these two earthquakes, the impact on Christchurch, as well as more general seismological questions. So over to you.
Yeah, just a general overview. I'm curious, what in terms of the science would you have liked to have had beforehand that you did not have in terms of instrumentation, time resources, etc., for better forecasting the probability of an event like this in terms of risk maps spatially?
Well, I mean, you know, obviously with hindsight, it's always, you can say we like this or that, but it's something we can learn from. I think the issue here is complicated also by the fact that when you look at the, you know, the history of seismicity in the area, I mean, this is an area that does not have a significant background level of seismicity. I mean, we've all shown different maps of different time intervals, but basically there have been no significant meaning like magnitude 3s or 4s in this region over the last period of time. And so it raises a question about, you know, like, yes, with resources it would be great, but how do you know, partition those into areas when within the country there are areas that are having a background level of seismicity that's more significant. So, you know, short of being able to instrument the entire landmass at a very high precision, it becomes a very difficult question of prioritizing.
Bill or Caroline, would either of you like to comment?
I would just like to add that we've been extremely fortunate to have a dense network of strong motion stations available for the Darfield earthquake and for the Christchurch earthquake. And yeah, it's just an invaluable network. Also, New Zealand, just to remind you that New Zealand is a small country with only a population of 6 million people. And so the resources are quite, you know, not as high as other bigger countries. And for such a small country, we have an amazing modern GeoNet network. So we do have very good source of data set. Thank you.
Okay, I think there's another question over here.
Yeah, actually, I had two questions. One was almost the same, and I would like just to add a comment, because I don't think that we can answer to this question only with seismological instruments and data, because the background here before was simply zero. And maybe the necessary interval time for observation is simply too long. So we must try to install a different kind of approach, maybe the SAR images with time series, which is pretty new approach, or continuous GPS data in order to try to match this very low strain rate. So I believe that the Christchurch earthquake is a key example of the limits of our forecasting. So that was just a comment to the Kevin answer. My second question concerns the questions that Kevin put on the table. because I believe that we have to be honest that to answer to these questions, seismologists or solid earth scientists can only provide a part of the answer. Because now for Christchurch, the problem is to engineering seismology, and the problem is how much does it cost to rebuild a city with 2.9 G due to any of the effects that the second speaker has shown. Because we still don't know which is the relative weight of this, directivity, liquefaction, site effects, stress drop, rupture velocity, and so on. All these effects can produce incredible shaking and will be very difficult even to distinguish which is dominating to a spatial scale. So we have to be honest to say that to answer to these questions, we need now to provide a more accurate kind of observations. And for seismology, the key question is, are our predictive relation for seismic earth assessment reliable, close to the false? And then this is the kind of answer they can provide, because to the question that Kevin raised, this is now a matter of engineering seismology. We are doing the best we can do.
Okay.
Yeah, may I just add quickly that although the modern buildings that were designed to sustain some really strong shaking did perform really well during the 6.3 earthquake, they're still at the moment, with the engineers in New Zealand have started to review the building standards. And so there will be some changes in the New Zealand building codes following that earthquake.
I just want to add one answer about the possibility of having data about the period before the first event, and we are collecting all the images from all the radar satellites available, L-band, ELOS data mainly, and MVSAT C-band to go through the time series analysis of the pre-seismic period.
Okay, I think we have a comment from the New Zealand ambassador here.
Hello. Let me just start by thanking the European Geosciences Union very much for arranging this event and for inviting me to participate in it. I found it extremely interesting, and I'd like to thank all the presenters. I think it's encouraging that so much data is available and progress has been made in the scientific understanding of the earthquake. And international cooperation is playing a big part in this, just as it did in the immediate rescue and recovery phase. In fact, the help we received from many other countries was critical at that time. I'm struck by the human aspects of this, you know, the loss of life and the human suffering and hardship and destruction that underlies some of this scientific data. So many questions are being asked, and as Kevin Furlong said, there are gaps. But the loss of life, as I think Carolina said, could have been much worse if the building codes and standards hadn't been higher in New Zealand. And I think that was demonstrated particularly by the Darfield earthquake in last September. The government has set up a royal commission to look into the reasons for the severe damage, particularly to buildings, and to review the adequacy of building codes and standards. So they have been asked to report on an interim basis within 6 months, and a final report in approximately 12 months' time. And in addition, other steps have been taken, including a panel of experts to look at the most badly damaged buildings, the reasons why they didn't perform better in this extreme situation. In addition, a minister has been appointed for the Canterbury earthquake recovery, and a standalone government department has been set up to support him. So without wanting to minimize the local impact of this event and the human dimension of it, a lot of progress has been made in the last 6 weeks, both on the scientific front and in restoring essential services, which are now virtually in place again, and in setting up the institutional arrangements to coordinate a longer-term recovery. I think it's very important that these steps are taken to restore confidence on the part of the people who have been through this experience. And I should say that, as I think some of the presentations have brought out, it was a severe but a relatively localized event. And Christchurch International Airport is fully operating as a gateway to the South Island, which is operating as normal at this point. Thank you.
Any questions? All right, just behind you there.
The big question that faces the politicians and decision makers in Christchurch is really what sort of seismic event should we have in mind when we make decisions about where to rebuild certain facilities, how to rebuild them, should certain suburbs be rebuilt or not. Now, what we've heard from the scientists so far is there's a lot of stuff they don't know. I would like to ask them to kind of cast aside the scientific robes for a moment and indicate as best they can in their personal opinions what sort of seismic shaking scenario should be on the table when the decisions of whether, where and how to rebuild are taken. In other words, for the next 100 years or even 200 years, what sort of shaking should Christchurch be expecting?
Well, I mean, none of us probably can answer this directly.
Actually, we have a slide.
Yeah. But I mean, I can give you, I think, while Bill's getting his slide up, I think one of the things we can think about is, as my first mentor in geology said, if you can see it, it can happen. And I think we now know certainly a minimum level of what can happen. We have seen it. And so I think it's very important to recognize that even in an area that otherwise might have been considered low probabilistically or low absolute value, this now becomes a minimum value that we have to plan for, that we have to be able to say, the Christchurch fault is not a very big fault, probably 10 kilometers plus or minus. It's a order magnitude 6 earthquake. These are hundreds and hundreds of those happen every year. So we're looking at something that is not an unlikely event somewhere. Exactly where is uncertain. So I think in answer to Tim's question, the first order thing is to say we're starting at what we have observed, and we then have to maybe give us some comfort zone above that, but it would be probably not, at least not scientifically acceptable to say some value less than what we observed, is my personal opinion.
Sorry, Tim, it's difficult for me to disrobe my science robe in response. But we actually do have a very good team of statistical seismologists that calculate conditional probabilities. And they combine actually a few different statistical calculations and statistical methods into one model that has as well as we know, the active fault database, that has information about recurrence intervals of faults, that has information about the aftershock sequence, and they're very good at generating probabilistic scenarios of the probability of exceeding a certain ground motion within a given period of time. So I think if you want to look at the building codes universally, you need to understand probabilities in any location relative to the other locations, and you need to really give that information to the lawmakers and then have them decide what is financially feasible to do, what's humanistically feasible to do. But we can provide some numbers to them to help them in the process.
Okay, question here in the middle.
This is really a question for the ambassador, I think. Christchurch is in many ways very analogous to a European city in the way it's built, more analogous than, for example, a city in the United States would be. I'm astonished not by what fell down, but by what did not fall down, including masonry buildings. And I was wondering, are there discussions going on between New Zealand and the European Commission about the example here, both in the preparation before the earthquake, and secondly in the response, which has been remarkably good. I think New Zealand has an awful lot to teach Europe here. And are you actually talking to the Commission? And I think the Commission should be talking to you.
Thank you very much. I'm not aware of any specific process underway to share information with the Commission, but I'm sure New Zealand would be very open to this. And I would imagine that there is a lot of international interest in this event and in the aftermath. And I would expect that a dialogue does take place, and certainly New Zealand would be very happy to share the lessons it's learned, and also the institutional arrangements that we have in place. I think Bill Fry commented on the open, direct and open lines of communication between the GNS, between the scientists and the policy makers. And I think in a relatively small country, it's probably easier in a way to integrate the various agencies which are responding to an emergency like this. In fact, a state of national emergency is still in place and has been extended to the 12th of April. And there are well-developed mechanisms for coordinating both central government, all central government agencies, and local government and emergency services, as well as offers of international assistance that are received.
Thank you. Next question in the middle here at the back, to your left.
I was more wondering about the immediate actions you're actually going to apply now, because from my understanding, most of this damage in the second earthquake and the February one were due to weakened building structure due to the September earthquake. And I've been actually down in Christchurch about 2 weeks after the first quake, and there was so little damage. I was really stunned how little damage, in fact, there was on buildings all across the city. So now it's of course far worse, but you sort of have to be prepared for a strong earthquake, at least of the magnitude around 6, let's say. So is there actually planned that buildings, mainly in the CBD where most of the damage is observed, to rebuild most of the buildings and really apply actually really strong measure on what is a very dangerous level of damage on the building structure?
I may be able to give you some insight. I've been at several meetings over the last several weeks with various of the engineering groups, IPENS, the Petroleum Professional Engineers of New Zealand, Society, etc. And I think one of the things that they are focused on, the structural engineers and the geotechnical engineers, is actually going into many of these buildings that may appear to be fine after these events, and do very detailed, much more detailed than maybe previously was traditional, analyses of the structural state of the buildings, to be able to make decisions on yes, they did their job exactly right, which is not to fall down, not to injure or kill people, but the question is, are they, should they now be retired? They've done their job, they've earned their pension, or should they be strengthened, or are they in fact quite all right? And so much more of looking in the innards of the structural strength of the building. So the engineering community, through several of the societies and through government agencies, are going to be trying to really analyze beyond simply, yes, this building doesn't have any cracks, so it looks okay. Much more detailed analyses.
One of the previous questioners asked this very poignant question about what scientists should do in terms of preparing better for the next earthquake in New Zealand. It seems to me that, first of all, a very considered approach of deciding what the implications of
this particular earthquake are for building codes and preparedness in New Zealand is important. But in the context of the recent Japanese earthquake, a broader assessment that would seem to be appropriate not only for New Zealand but for areas like California where I live. The international community of scientists will be sifting and evaluating the data from both of these earthquakes for several years to come. And the implications, first of all, for the science will take a while for all the dust to settle and consensus to emerge. And then translating that into public policy will take a little bit longer, it seemed to me, and that would be entirely appropriate. And as scientists, that's part of our job too.
Just to echo Wayne's comments, as an outsider who happens to be in New Zealand during this time as a visiting faculty member, I take home, both, I love the country and I've spent a lot of great time there, but I also see the implications of this globally for other places. And I think, it's a very sobering lesson, I think, that I'm taking home from the Canterbury events, in that these are not in a global world, particularly large earthquakes. These are earthquakes that are relatively common. Earthquakes of this size, earthquakes of these characteristics are relatively common globally, and yet we see that a modern city can be laid low by these events. And so I think the lesson to take to California, to many places in North America, in Europe, in the Mediterranean area, of the potential impacts of magnitude 6 earthquakes is really important. And that's, in a sense, maybe a bigger lesson from this than what is needed. New Zealand is quite aware, and there's no question about educating the politicians or anyone else there about the significance of this event. We may need to help, as scientists, educate our policymakers in our own countries that magnitude 6 earthquakes can be deadly, and we need to be very conscious of that.
Can I add a comment on another thing I've personally learned is that we as scientists, we're very hesitant to make absolute firm conclusions. I think part of the scientific process and part of what makes us scientists is that we're very skeptical. And when you're in a situation like this, you need to make definitive decisions, and you need to get them out very, very quickly. And a way we can prepare for something like this in the future is we can understand in our daily research careers that, well, we need to find a stopping point and say that this is the procedure we're going to take if there's something like this come up again, and we're not going to just treat it like we do the rest of our research, saying, well, we still want to experiment a little more, we still want to find out, we still want to be a little more certain about something. So we need to have hard methods just coded in where we know exactly how to act and how to respond in situations like this scientifically.
One question here in the middle.
For many parts of Europe, I find the Christchurch event very scary, because with the moderate seismicity we got in many countries in Northern Europe, we ought to work better on scenarios, also in areas with relatively low seismicity, and we don't actually have the resources to go back and work back on scenarios for any given area, say update scenarios in even improbable areas every 5 years. There's simply not the number of people available in some countries, sometimes not even the expertise, because of the very long return time on even moderate earthquakes. So I think, again, it is a very sobering experience, and I think there is an issue of resources as well to look at recurring scenarios.
Does anybody else want to comment on this aspect here?
Yeah, I would like to add just a comment on this issue. And again, I believe that here we are moving from our capability to get robust, corroborated, validated scientific results to operational actions. And the scientists are only one of the possible actors. And the best we can do is to assess probability, is to try to identify the strain rate, the fault activity, the background seismicity, the change in seismicity rates, and to transfer this information in a way in which operational forecasting can be achieved. But we are only one of the chain, one part of the chain, because to transfer scientific results into operational decisions, it is much more difficult and is not our duty. And I will make two examples. The first example concerns the scenarios. If we elaborate the worst case scenario for a urban area, this is useless. If you do this to Istanbul, I make the example of Istanbul because it's more familiar to me, and if you do the worst case scenario for the Marmara Sea fault, you will have more than 2G, and you have nearly 60% of the buildings that will collapse in Istanbul. What you can do? You should evacuate the city and simply to escape. If you do this to an engineer, the engineer will tell, no thanks, this is not you, I can do nothing with this. And the second example is the decision that we can do with the forecasting, with the probability. Because even the giant Japanese earthquake, if you compute the probability of a magnitude larger than 8, was 5%. For a magnitude larger than 8, 5% is huge. But this is a scientific results. How can be translated into actions? And in Italy, we have the experience of the L'Aquila earthquake, which was practically, which has also legal and a prosecution that is going on because the limit between the science and the operational was not well established. And this created a loss of credibility of the scientists to the society. So we have to be honest that we are only doing, so the best we can do is to improve our results, to make our results available and useful for the engineering community, and to try to do the best action for outreach. This is the best we can do.
Just to follow on that last point, I think it's very important, both the communication we have with our sister organizations or sister groups that are technically oriented, the engineers, the structural engineers. But the point about the outreach is, I think, really important, that the science community, the earth science community, should be taking a leadership role when events like these happen to help the public and policymakers. I mean, most policymakers under background in the earth sciences would be probably very similar to the general public's rather than most of the people in the room here. But it's, I think, our obligation to be providing outreach to the general public to help them understand what is happening. And I can tell you the experiences I've had, both as a visitor, but giving public lectures on these events, and even most recently on the Japanese event at universities and in towns in New Zealand, has been overwhelming. The information, the thirst for information that the general public has is huge. And they value getting it from our community, not filtered through 3 levels of media and newscasters, et cetera. But so I think, a message I would say to everyone in the room is, if you haven't done it yet, go back to your home place and schedule a public lecture on the recent earthquakes that have been occurring around the world to help the general public understand what's going on.
Okay, I think that's probably a very good place to draw this to a close, particularly as we have to participate in a press conference shortly. So thank you everybody very much indeed for coming. Don't forget the poster session tomorrow morning, and just remind you also as an advertisement that there are sessions tomorrow on the Japan earthquake. So you can see all the details by going to the EGU front page. Follow the links there. Thank you very much for attending.